clear night, far from the glow of city lights, the sky reveals a vast canopy of stars scattered across the darkness. To the unaided eye, these points of light appear small, steady, and silent. Yet each one is a colossal sphere of glowing gas, radiating energy across immense distances. The stars visible from Earth are only a tiny fraction of those that exist within our own galaxy, the Milky Way, which contains hundreds of billions of stars. Beyond it lie billions of other galaxies, each filled with their own stellar populations, stretching the scale of the universe beyond ordinary comprehension. A star is a massive, luminous sphere composed primarily of hydrogen and helium. Deep within its core, immense pressure and temperature enable nuclear fusion, a process in which hydrogen nuclei combine to form helium, releasing vast amounts of energy. This energy travels outward through the star's layers before escaping into space as light and heat. The steady glow seen from Earth is the result of this continuous release of energy, often sustained for millions or billions of years. The nearest star to Earth is the Sun, located about 150 million kilometers away. Its light takes approximately 8 minutes to reach our planet. By comparison, the next closest star system, Alpha Centauri, lies over 4 light-years away. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. These distances illustrate why stars appear so small and faint, despite their enormous size and brightness. Stars vary widely in size, temperature, color, and brightness. Some are smaller than planets, while others are hundreds of times larger than the Sun. Their colors reveal their surface temperatures. Cooler stars emit a reddish glow, while hotter stars shine white or blue. This range of colors can sometimes be observed with the naked eye under dark skies, adding subtle variation to the night's appearance. Brightness, as seen from Earth, depends on both a star's intrinsic luminosity and its distance. A nearby star of modest brightness may appear more prominent than a distant but extremely luminous one. Astronomers measure apparent brightness using a scale called magnitude, where lower numbers represent brighter objects. Negative magnitudes indicate exceptional brightness, as seen with Venus or certain prominent stars. Stars are not randomly scattered. Many form recognizable patterns known as constellations, which have been used for navigation and storytelling across cultures for thousands of years. While the stars in a constellation may appear close together from Earth's perspective, they often lie at vastly different distances in space. The patterns are a result of human perception rather than physical grouping. Beyond constellations, stars often exist in true groupings called clusters. Open clusters are loose collections of stars that form together and remain bound by gravity. Globular clusters are dense, spherical assemblies containing hundreds of thousands of stars, tightly packed and orbiting the outskirts of galaxies. These clusters provide valuable insights into stellar behavior and galactic structure. The life of a star is governed primarily by its mass. More massive stars burn hotter and brighter, but consume their fuel more quickly. Smaller stars burn more slowly and can shine for far longer periods. This balance between mass, gravity, and energy production determines a star's characteristics and longevity. Although individual lifespans vary greatly, the processes governing stars follow consistent physical principles throughout the universe. From Earth, the steady light of stars may appear timeless, However, the light reaching our eyes often began its journey years, centuries, or even millennia ago. Observing the night sky is therefore an act of looking into the past. Some stars visible today may no longer exist in their original form, their light continuing to travel long after changes have occurred. Modern astronomy uses advanced instruments to study stars across many wavelengths, including visible light, infrared, ultraviolet, and radio waves. Each portion of the electromagnetic spectrum reveals different aspects of stellar structure and behavior. Through these observations, astronomers can determine a star's composition, temperature, motion, and distance, deepening our understanding of the cosmos. Despite the scientific knowledge gained over centuries, the sight of stars continues to inspire quiet reflection. Their immense distances and enduring light offer a sense of scale and continuity that contrasts with the brief span of human experience. In the stillness of the night, the presence of countless stars serves as a reminder of the vast and orderly universe beyond our world. Across the vast expanses of galaxies lie immense clouds of gas and dust known as nebulae. These regions, often spanning dozens or even hundreds of light years, serve as the birthplaces of stars. Though they appear faint and delicate through telescopes, nebulae contain enough material to form thousands of stars. Within these cold, dark clouds, gravity quietly begins its work, drawing particles together over immense spans of time. Nebulae are composed primarily of hydrogen, the most abundant element in the universe, along with helium and trace amounts of heavier elements. Temperatures within these clouds can be extremely low, often only a few degrees above absolute zero. In such conditions, atoms move slowly, allowing gravity to gradually pull the gas and dust into denser regions. These dense pockets, called molecular cloud cores, mark the earliest stage of star formation. As a cloud core accumulates mass, its gravitational pull strengthens. Material continues to fall inward, increasing both pressure and temperature at the center. Over thousands to millions of years, the collapsing region becomes a protostar, a young stellar object not yet hot enough to sustain nuclear fusion. During this stage, the protostar is often surrounded by a rotating disk of gas and dust, known as a protoplanetary disk. Within this disk, smaller structures may eventually form, including planets, moons, and other bodies. The collapse of a protostar is not a violent event, but a gradual process shaped by balance. Gravity pulls inward, while pressure from heated gas pushes outward. As material continues to fall toward the center, the temperature rises steadily. When the core temperature reaches several million degrees Celsius, hydrogen nuclei begin to fuse into helium. This marks the moment a true star is born. The energy released by fusion creates outward pressure that halts further collapse, establishing a stable balance between gravity and radiation. Young stars often emit strong stellar winds and radiation that shape their surrounding nebulae. These outflows can carve cavities and produce glowing regions where ultraviolet light excites nearby gas. The brilliant colors seen in emission nebulae arise from this interaction, with hydrogen producing red hues and oxygen contributing shades of green or blue. These glowing clouds provide visual evidence of ongoing star formation, Star formation rarely occurs in isolation. Most stars form in clusters within the same nebula, sharing a common origin. Over time, gravitational interactions and galactic motion may disperse these clusters, sending stars drifting into different regions of the galaxy. The Sun is believed to have formed in such a cluster billions of years ago, though its stellar siblings are now widely scattered. Not all collapsing cloud cores become stars. Some lack sufficient mass to ignite sustained fusion and instead form brown dwarfs. These objects occupy a middle ground between planets and stars. They emit faint infrared radiation due to residual heat from their formation, but never achieve the core temperatures required for long-term hydrogen fusion. Brown dwarfs provide valuable insights into the lower limits of star formation. The efficiency of star formation within nebulae varies widely. In many regions, only a small fraction of the available gas becomes stars. Stellar winds, radiation, and shock waves from nearby stellar activity can disrupt the surrounding material, halting further collapse. Conversely, shock waves from events such as supernova explosions can compress gas clouds, triggering new waves of star formation. In this way, the life cycles of stars are interconnected across time and space. Astronomers study star-forming regions using a range of observational tools. Infrared telescopes can peer through dense dust clouds that block visible light, revealing hidden protostars and disks. Radio observations detect molecular emissions that trace the distribution of cold gas. By combining data across wavelengths, scientists construct detailed models of stellar birth, improving our understanding of how stars emerge from interstellar matter. The timescale for star formation is immense by human standards. From the initial collapse of a cloud core to the ignition of fusion, the process may take millions of years. Yet on cosmic timescales, star formation is continuous, replenishing galaxies with new sources of light and energy. Even now, within distant nebulae, countless protostars are forming, each destined to shine for millions or billions of years. The quiet creation of stars within nebulae underscores the dynamic nature of the universe. What appears as a static night sky is, in reality, a changing landscape shaped by gravity, radiation, and time. The light from young stars emerging from their dusty cradles travels across space, eventually reaching observers who may never witness the process directly, but can trace its effects through careful study. In the stillness of space, star formation proceeds without sound or haste. The gradual gathering of matter, the rise of temperature, and the onset of fusion unfold over ages beyond ordinary perception. Yet the result is familiar: the steady glow of a new star, joining countless others in illuminating the vast darkness of the cosmos. A star may appear as a simple point of light, yet beneath its glowing surface lies a complex internal structure governed by pressure, temperature, and energy transfer. From its dense core to its outer atmosphere, each layer of a star plays a role in maintaining the balance that allows it to shine steadily for vast spans of time. Understanding these layers reveals how stars generate and transport the energy that eventually reaches distant worlds. At the very center lies the core, the engine of the star. Here, Temperatures can reach millions of degrees, and pressure is immense due to the weight of the overlying layers. Under these extreme conditions, nuclear fusion occurs as hydrogen nuclei combine to form helium. This process releases energy in the form of gamma rays and kinetic motion of particles. Surrounding the core is the radiative zone, a region where energy moves outward primarily through radiation. Photons generated in the core are absorbed and re-emitted countless times by surrounding particles. This process is slow and indirect. A photon may take thousands or even millions of years to travel from the core to the outer layers. The dense plasma in this region ensures that energy transfer occurs through repeated interactions rather than direct movement. Beyond the radiative zone lies the convective zone. In this layer, energy is transported through convection, a process similar to the circulation of heated fluid. Hot plasma rises toward the surface, cools, and then sinks back inward to be reheated. This continuous motion creates vast convection cells within the star. In the Sun, these motions contribute to surface patterns known as granulation, visible through high-resolution solar observation. At the very center lies the core, the engine of the star. Here, temperatures can reach millions of degrees, and pressure is immense due to the weight of the overlying layers. Under these extreme conditions, nuclear fusion occurs as hydrogen nuclei combine to form helium. This process releases energy in the form of gamma rays and kinetic motion of particles. Surrounding the core is the radiative zone, a region where energy moves outward primarily through radiation. Photons generated in the core are absorbed and re-emitted countless times by surrounding particles. This process is slow and indirect. A photon may take thousands or even millions of years to travel from the core to the outer layers. The dense plasma in this region ensures that energy transfer occurs through repeated interactions rather than direct movement. The outermost layer of a star's atmosphere is the corona, an expansive region of extremely hot, thin plasma extending millions of kilometers into space. Despite its low density, the corona can reach temperatures of several million degrees. It emits energy primarily in ultraviolet and X-ray wavelengths. The mechanisms that heat the corona to such high temperatures are complex and involve magnetic fields and plasma interactions. Magnetic fields play a significant role in shaping stellar behavior. Generated by the movement of charged particles within the star, these fields can create sunspots, flares, and loops of glowing plasma. Sunspots are cooler, darker regions on the photosphere associated with intense magnetic activity. Their number and distribution vary over time, reflecting cycles of magnetic activity that can influence the surrounding space environment. Energy generated in the core ultimately escapes through the outer layers, radiating into space as electromagnetic waves. This energy supports the star against gravitational collapse by providing outward pressure. The balance between gravity pulling inward and energy pushing outward is known as hydrostatic equilibrium. As long as this balance is maintained, the star remains stable. Different types of stars exhibit variations in internal structure. In smaller stars, convection may extend deeper into the interior, while in massive stars, the convective and radiative zones may be arranged differently. These structural differences influence how energy is transported and how long the star can sustain fusion. By studying these variations, astronomers gain insights into stellar life cycles and the diversity of stars throughout the universe. Observations of stellar structure rely on indirect methods. Scientists analyze light spectra, surface oscillations, and magnetic activity to infer internal conditions. Helioseismology, the study of vibrations within the Sun, has provided detailed information about its internal layers. Similar techniques are applied to other stars, allowing astronomers to compare their structures despite vast distances. The layered nature of stars reflects the fundamental forces at work within them. Gravity compresses matter inward, while fusion-generated energy pushes outward. Between these forces, energy moves through radiation and convection, eventually emerging as light. Though invisible to the naked eye, the internal structure of a star determines its brightness, temperature, and lifespan. The steady light seen from Earth is the final step in a long journey that began in the core, traveled through dense plasma, and escaped into the vacuum of space. The stars that fill the night sky appear similar at first glance, yet careful observation reveals subtle differences in color and brightness. These variations are not random. They reflect fundamental physical properties such as temperature, size, and energy output. By studying the light emitted by stars, astronomers have developed classification systems that organize them into categories, allowing patterns and relationships to emerge from what once seemed like a scattered collection of lights. A star's color is closely linked to its surface temperature. Cooler stars emit light that appears red or orange, while hotter stars shine white or blue. This relationship arises from the way heated objects radiate energy. As temperature increases, the peak wavelength of emitted radiation shifts toward the blue end of the spectrum. This principle, known as blackbody radiation, applies to stars as well as to heated materials on Earth. Red stars, among the coolest, have surface temperatures of about 2,500 to 3,500 degrees Celsius. They often appear faint to the naked eye, though some are large and luminous, despite their lower temperatures. Orange and yellow stars occupy a middle range, with temperatures between roughly 4,000 and 6,000 degrees Celsius. The Sun falls within this category, emitting a steady yellow-white light that supports life on Earth. White stars are hotter still, while blue stars, among the hottest, can exceed 20,000 degrees Celsius at their surfaces. Brightness is another key characteristic. Apparent brightness measures how bright a star appears from Earth, while absolute brightness, or luminosity, measures its true energy output. A star may appear dim because it is distant, even if it is intrinsically very bright. Conversely, a nearby star may appear prominent despite modest luminosity. Astronomers use standardized measurements to distinguish between these effects. The Hertzsprung-Russell diagram, often abbreviated as the HR diagram, is a powerful tool for understanding stellar properties. This chart plots stars according to their luminosity and surface temperature. Most stars fall along a diagonal band known as the main sequence, where they spend the majority of their stable lifetimes. More luminous and cooler stars occupy the upper right region as giants and supergiants, while hot but faint stars, such as white dwarfs, appear in the lower left. Star color can sometimes be detected without instruments. Under dark skies, attentive observers may notice that some stars appear reddish, while others have a bluish tint. Betelgeuse, for example, shows a warm red hue, while Rigel appears blue-white. These color differences reflect the underlying temperatures and provide a visual reminder of the diversity among stars. Interstellar dust can also affect the perceived color of stars. Dust particles scatter shorter wavelengths of light more effectively than longer wavelengths. As a result, distant stars may appear redder than they truly are, a phenomenon known as interstellar reddening. Astronomers account for this effect when analyzing stellar spectra to ensure accurate classification. Binary and multiple star systems add further complexity. In such systems, two or more stars orbit a common center of mass. If the stars differ in temperature and luminosity, their combined light may produce unusual colors or spectral features. Careful analysis allows astronomers to separate these contributions and study each star individually. The classification of stars is not static. As observational technology improves, new details emerge, refining our understanding of stellar properties. Large-scale surveys using space telescopes and ground-based observatories continue to catalogue millions of stars, expanding classification systems and revealing subtle variations within established categories. By examining stellar colors, temperatures, and spectra, astronomers gain insight into the physical processes that govern stars. These observations connect distant points of light to measurable properties, transforming the night sky into a structured and meaningful landscape. The quiet glow of stars thus becomes a record of temperature, composition, and energy, encoded in the light that travels across space to reach observers on Earth. Stars are often perceived as permanent fixtures in the night sky, shining with steady light year after year. In reality, each star exists within a long but finite lifespan, shaped primarily by its mass. From the moment nuclear fusion begins in its core, a star enters a prolonged period of stability, balancing gravity and energy output. This phase, known as the main sequence, accounts for the majority of a star's life and determines its long-term behavior. The stability of a star depends on hydrostatic equilibrium, the balance between inward gravitational force and outward pressure from energy produced by nuclear fusion. Gravity continuously pulls matter toward the core, while the energy released through fusion pushes outward. As long as these forces remain balanced, the star maintains a consistent size, temperature, and luminosity. Even slight changes in this balance trigger adjustments within the star, restoring equilibrium. Mass plays the central role in determining how long a star can sustain fusion. Massive stars contain greater amounts of hydrogen fuel, but consume it at a much faster rate due to higher core temperatures and pressures. These stars burn brightly and live relatively short lives, sometimes only a few million years. Smaller stars, by contrast, fuse hydrogen more slowly and can shine for tens or even hundreds of billions of years, far exceeding the current age of the universe. Red dwarf stars, the smallest and most common type, exemplify stellar longevity. With low masses and efficient energy use, they burn their hydrogen fuel gradually. Their fully convective interiors allow hydrogen from outer layers to circulate into the core, prolonging fusion. As a result, red dwarfs remain stable for immense periods, emitting steady, faint light. None have yet reached the final stages of their lifespans, as the universe itself is not old enough. Stars similar in mass to the Sun have lifespans of roughly 10 billion years. During the main sequence phase, they convert hydrogen into helium in their cores at a steady rate. Over time, helium accumulates, gradually altering the core's composition. Although this process unfolds over billions of years, it eventually leads to structural changes that mark the end of the main sequence phase. For now, the Sun remains in a stable middle period of its life. Massive stars live dramatically different lives. With masses many times greater than the Sun, their cores reach extreme temperatures, enabling fusion of heavier elements beyond hydrogen and helium. Their intense energy output creates strong stellar winds that carry material into space. These stars shine with brilliant blue light, but exhaust their fuel rapidly. Their short lifespans illustrate the trade-off between brightness and longevity. Stellar rotation also influences stability. Many stars rotate on their axes, with speeds varying widely. Rapid rotation can cause equatorial bulging due to centrifugal force, altering surface gravity and temperature distribution. Magnetic fields generated by rotating plasma can produce star spots and flares, affecting energy output on smaller scales. Despite these variations, the overall stability of a star remains governed by the balance between gravity and fusion. Binary star systems present additional complexities. When two stars orbit closely, their gravitational interaction can affect mass distribution and stability. In some cases, material flows from one star to another, altering their evolution. These interactions can lead to phenomena such as accretion disks and sudden increases in brightness. Such systems provide valuable opportunities to study how stars respond to changing mass and gravitational conditions. Stellar winds, streams of charged particles flowing outward from a star's atmosphere, contribute to gradual mass loss over time. In smaller stars, this loss is minimal and does not significantly affect stability. In massive stars, however, strong winds can remove substantial amounts of material, influencing their lifespans and the surrounding interstellar environment. The expelled material enriches space with elements that may later become part of new stars and planetary systems. Magnetic activity cycles can cause periodic changes in a star's surface features and energy emissions. The Sun, for example, exhibits an approximately 11-year cycle marked by fluctuations in sunspot numbers and solar flares. These cycles reflect the dynamics of magnetic fields generated within the convective zone. Although such activity can influence nearby space environments, it does not significantly alter the star's overall stability. The concept of stellar equilibrium extends across all star types. Whether large or small, hot or cool, stars maintain their structure through the continuous interplay of forces. This balance allows them to radiate energy steadily across immense distances, providing light and heat that may influence surrounding systems. The enduring glow of stars is therefore not static, but the result of constant adjustment and balance. From a human perspective, stellar lifespans are almost incomprehensibly long. Entire civilizations rise and fall in the time it takes for a star to undergo minor internal changes. The light reaching Earth tonight began its journey years or centuries ago, carrying evidence of conditions that may already have evolved. Observing stars is thus both a glimpse into the present and a record of the past. The stability of stars offers a sense of continuity in an ever-changing universe. Though individual stars are born and eventually fade, the processes that sustain them remain consistent. Across galaxies and cosmic time, stars continue to shine, governed by the same physical laws that maintain their balance. In the quiet persistence of their light, they embody both endurance and change on a scale far beyond ordinary experience. Not all stars remain the same size throughout their lifetimes. As stars exhaust the hydrogen fuel in their cores, many undergo dramatic changes, expanding into giant or supergiant forms. These immense stars, far larger than their earlier main sequence stages, represent a later phase of stellar development marked by altered energy production and shifting internal structures. Their vast sizes and luminous appearances make them some of the most striking objects in the night sky. When a star similar in mass to the Sun depletes hydrogen in its core, fusion slows, and the outward pressure that once balanced gravity begins to diminish. Gravity causes the core to contract, increasing its temperature and pressure. Meanwhile, hydrogen fusion continues in a shell surrounding the core. The increased energy output from this shell pushes the outer layers outward, causing the star to expand enormously. As the surface spreads over a larger area, it cools, giving the star a reddish appearance. At this stage, the star is known as a red giant. Red giants can grow to hundreds of times the Sun's original diameter. If placed at the center of our solar system, some would extend beyond the orbit of Earth. Despite their cooler surface temperatures, their immense size makes them highly luminous. Their extended atmospheres are often unstable, and they may lose mass through stellar winds that carry material into surrounding space. This expelled matter contributes to the interstellar medium, enriching it with heavier elements. More massive stars undergo similar expansion, but on a far greater scale. These stars become supergiants, among the largest stars known. Red supergiants, such as Betelgeuse, can reach diameters hundreds or even over 1,000 times that of the Sun. Their outer layers are tenuous and extended, with complex convection patterns that create irregular brightness variations. Blue supergiants, on the other hand, are extremely hot and luminous, with intense radiation that shapes nearby interstellar material. The internal processes within giant and supergiant stars differ from those in main sequence stars. As core temperatures rise, fusion of heavier elements becomes possible. Helium nuclei may combine to form carbon and oxygen, releasing energy that temporarily stabilizes the star. In more massive stars, fusion can proceed through successive stages, producing elements such as neon, silicon, and iron. Each stage occurs over progressively shorter timescales, reflecting the increasing energy demands of heavier element fusion. The outer layers of giant stars are loosely bound by gravity, making them susceptible to pulsations. These rhythmic expansions and contractions cause variations in brightness that can be observed from Earth. Variable stars, including Cepheid variables, play an important role in measuring cosmic distances. Their predictable brightness cycles allow astronomers to determine their intrinsic luminosity and calculate distances to faraway galaxies. Mass loss is a defining feature of giant and supergiant stars. Powerful stellar winds and pulsations eject material into space, forming expanding shells of gas and dust. In some cases, this material creates beautiful structures known as planetary nebulae, illuminated by the remaining core of the star. These nebulae, despite their name, have no relation to planets. The term originated from their round appearance in early telescopes. Supergiant stars have relatively short lifespans compared to smaller stars. Their enormous energy output consumes fuel rapidly, leading to dramatic changes over millions rather than billions of years. Their intense radiation and strong winds shape the surrounding interstellar environment, influencing future star formation. In this way, giant stars contribute to the ongoing cycle of matter within galaxies. The colors of giant stars reflect their surface temperatures. Red giants appear cool but luminous, while blue supergiants emit brilliant blue-white light due to their extreme heat. Observations of these colors, combined with spectral analysis, provide insight into their composition and internal processes. By studying giant stars, astronomers gain a deeper understanding of how stars evolve beyond the main sequence. The scale of these stars challenges ordinary perception. A supergiant's surface gravity is much weaker than that of a smaller star, despite its immense mass, because its outer layers are so widely spread. This low gravity allows material to escape more easily, contributing to the formation of surrounding nebulae. The tenuous atmospheres of supergiants can extend vast distances, blending gradually into the interstellar medium. From Earth, some giant stars are visible as prominent points of light. Betelgeuse in the constellation, Orion, and Antares in Scorpius display reddish hues that distinguish them from other stars. These colors offer a visual reminder that stars are not uniform, but exist in various stages of development. Their gentle glow reflects complex processes unfolding over immense timescales. The transition from main sequence star to giant or supergiant represents a natural stage in stellar life cycles. As fusion processes change and internal structures adjust, stars expand and transform. These changes, though gradual on cosmic timescales, reshape the star's appearance and influence its surroundings. The expanding atmospheres and enriched material they release become part of the broader galactic environment. In the quiet vastness of space, giant stars shine as beacons of transformation. Their immense forms and luminous presence mark a stage of stellar life, defined by change, expansion, and contribution to the cosmic landscape. Though their time in this phase is limited, their impact extends far beyond their own existence, shaping the matter and light that fill the universe. When stars like the Sun reach the end of their giant phase, they do not simply disappear. Instead, they shed their outer layers and leave behind a dense core known as a white dwarf. These stellar remnants represent one of the final stages in the life of many stars, preserving the mass of the original star in a compact form. Though small in size, white dwarfs remain extremely hot and continue to radiate energy for billions of years as they gradually cool. A white dwarf forms after a red giant expels its outer layers into space. This ejected material may create a glowing shell called a planetary nebula, illuminated by the intense radiation of the exposed core. As the nebula expands and fades, the remaining core becomes visible as a white dwarf. Despite the name, these objects can appear white, bluish, or even faintly yellow, depending on their temperature and age. The density of a white dwarf is extraordinary, with a mass comparable to that of the Sun compressed into a volume similar to Earth's. A teaspoon of white dwarf material would weigh several tons. This extreme density arises because the star's core has collapsed under gravity until electron degeneracy pressure halts further contraction. In this state, electrons are packed as closely as quantum mechanics allows, creating a stable structure that resists additional compression. White dwarfs no longer generate energy through nuclear fusion. Instead, they shine due to residual thermal energy retained from earlier stages. Over immense timescales, they radiate this heat into space and slowly cool. The cooling process can take billions of years, during which the white dwarf gradually dims. In theory, an ancient white dwarf could eventually become a cold, dark object known as a black dwarf, though the universe is not yet old enough for any to exist. The maximum mass of a stable white dwarf is limited by the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. If a white dwarf exceeds this limit, it can no longer support itself against gravitational collapse. In binary systems, a white dwarf may accumulate matter from a companion star. If sufficient mass is gained, this can trigger a thermonuclear explosion known as a Type 1 supernova, briefly outshining entire galaxies and dispersing elements into space. Not all stellar remnants are white dwarfs. Stars significantly more massive than the Sun may end their lives as neutron stars or black holes. Neutron stars form when a massive star's core collapses under gravity, compressing protons and electrons into neutrons. The result is an object of incredible density, with a mass greater than the Sun packed into a sphere only about 20 kilometers in diameter. These remnants often rotate rapidly and emit beams of radiation detectable as pulsars. Black holes represent an even more extreme outcome. When the core of a very massive star collapses beyond the limits supported by neutron degeneracy pressure, gravity overwhelms all other forces. The resulting object has a gravitational field so strong that not even light can escape from within a boundary known as the event horizon. Though invisible directly, black holes can be detected through their interactions with surrounding matter and their influence on nearby stars. White dwarfs provide valuable insight into stellar history. By measuring their temperatures and luminosities, astronomers can estimate their cooling ages. These measurements help determine the ages of star clusters and contribute to our understanding of galactic evolution. Because white dwarfs cool predictably over time, they serve as cosmic clocks that record the passage of billions of years. In binary systems, white dwarfs can exhibit dramatic behavior. As matter from a companion star accumulates on the white dwarf surface, pressure and temperature increase until a sudden burst of fusion occurs. This event, known as a nova, causes a temporary surge in brightness without destroying the star. Such events may recur if mass transfer continues, creating periodic outbursts observable from Earth. The surface gravity of a white dwarf is extremely strong, causing heavier elements to sink rapidly beneath the surface. As a result, their atmospheres are often composed of the lightest elements, hydrogen or helium. However, observations sometimes reveal traces of heavier elements, suggesting the accretion of material from surrounding debris or disrupted planetary bodies. These findings offer clues about the fate of planetary systems after their stars evolve. White dwarfs are common throughout the Milky Way. Because many stars share similar masses to the Sun, a significant portion of stellar remnants take this form. Though faint and difficult to observe individually, their collective presence contributes to the galaxy's overall structure. Surveys using sensitive instruments continue to identify and catalogue white dwarfs, expanding knowledge of their distribution and properties. Despite their small size, white dwarfs remain powerful reminders of the forces that shape stellar evolution. Their dense structure, gradual cooling, and occasional explosive behavior illustrate the varied outcomes that follow a star's active life. They represent stability in a different form, no longer fueled by fusion, but sustained by the principles of quantum mechanics and gravity. In the quiet darkness of space, white dwarfs persist as dim embers of former stars. Their fading light carries the history of nuclear fusion, expansion, and transformation. Though their brilliance has diminished, they endure for billions of years, marking the final chapters in the long and intricate lives of stars. Among the most extraordinary stellar remnants are neutron stars, objects formed when the cores of massive stars collapse under immense gravitational pressure. These remnants represent one of the densest forms of matter in the universe. Though only about 20 kilometers in diameter, a neutron star can contain more mass than the Sun. Its compact size and extreme density create conditions that challenge ordinary understanding and reveal the powerful forces at work in stellar evolution. Neutron stars form during the violent end of a massive star's life, when nuclear fusion can no longer support the core against gravity. The core collapses rapidly. Protons and electrons are forced together, forming neutrons and releasing a burst of neutrinos. This sudden compression halts when neutron degeneracy pressure, a quantum mechanical effect, resists further collapse. The outer layers of the star rebound off the compressed core, producing a supernova explosion that disperses material into space while leaving the neutron star behind. The density of a neutron star is almost unimaginable. A single teaspoon of neutron star material would weigh billions of tons on Earth. Matter exists in a state unlike anything found naturally on our planet. At such densities, atoms cannot remain intact. Instead, matter forms a tightly packed sea of neutrons. The interior structure may include layers of superfluid neutrons and superconducting protons, though many details remain subjects of ongoing research. Despite their small size, neutron stars possess extremely strong gravitational fields. A person standing on the surface would experience gravity billions of times stronger than on Earth. This intense gravity bends light and affects the motion of nearby objects. Even a slight disturbance in the surrounding space can lead to measurable changes in the neutron star's behavior, providing valuable data for astronomers studying gravity under extreme conditions. Many neutron stars rotate rapidly, conserving angular momentum from the original collapsing core. Some spin several times per second, while others rotate hundreds of times per second. These rapid rotations generate powerful magnetic fields that can be trillions of times stronger than Earth's. Charged particles accelerated along magnetic field lines emit beams of electromagnetic radiation from the magnetic poles. If these beams sweep past Earth, they are detected as regular pulses, giving rise to the term pulsar. Pulsars were first discovered in 1967 through their precise radio signals. Their regular pulses, sometimes accurate to within fractions of a millisecond, make them among the most reliable natural clocks in the universe. By studying pulsars, astronomers can test theories of gravity, measure distances in space, and even detect subtle disturbances caused by passing gravitational waves. Their steady signals provide a unique tool for exploring cosmic phenomena. The magnetic fields of neutron stars influence their surroundings in dramatic ways. Particles accelerated near the surface emit high-energy radiation, including X-rays and gamma rays. In some cases, neutron stars draw material from companion stars, forming accretion disks of heated gas. As this material spirals inward, it emits intense radiation before settling onto the neutron star's surface. These systems, known as X-ray binaries, are among the brightest X-ray sources in the sky. A special class of neutron stars, known as magnetars, exhibits magnetic fields even stronger than typical neutron stars. These fields can distort atomic structures and trigger sudden releases of energy called starquakes. The resulting bursts of gamma rays may briefly outshine entire galaxies in their energy output. Though rare, magnetars demonstrate the extreme range of behaviors possible among stellar remnants. Neutron stars gradually slow their rotation over time as they lose energy through radiation. This process, known as spin-down, allows astronomers to estimate their ages. Younger neutron stars rotate more rapidly, while older ones spin more slowly. By measuring rotation periods and changes over time, scientists gain insight into the life cycles of these compact objects. The surfaces of neutron stars are thought to be solid crusts composed of densely packed nuclei. Beneath this crust lies a superfluid interior where matter behaves in unusual ways, flowing without friction. Sudden shifts within this interior can cause glitches, abrupt changes in rotation speed observed in some pulsars. These events provide clues about the internal structure and dynamics of neutron stars. Neutron stars are relatively rare compared to other stellar remnants, as only the most massive stars produce them. However, their influence extends far beyond their small size. Their strong gravitational and magnetic fields shape surrounding space, affect nearby stars, and generate radiation detectable across vast distances. Observations of neutron stars contribute to our understanding of matter under extreme pressure and the fundamental laws of physics. From Earth, neutron stars are invisible to the naked eye. Their presence is revealed through radio signals, X-rays, and gamma rays detected by specialized instruments. Space-based observatories play a crucial role in studying these objects, capturing high-energy emissions that cannot penetrate Earth's atmosphere. Through these observations, scientists continue to uncover new details about neutron stars and their remarkable properties. In the silent depths of space, neutron stars stand as remnants of powerful transformations. Their compact forms and steady pulses serve as enduring markers of stellar endings. Though born in violent explosions, they persist as stable, rotating beacons, emitting rhythmic signals that traverse the cosmos. Their existence highlights the diverse outcomes of stellar life cycles and the extraordinary conditions found beyond our world. Among the most enigmatic outcomes of stellar collapse are black holes, objects formed when the core of a very massive star contracts beyond the limits supported by known physical forces. These regions of space possess gravitational fields so intense that nothing, not even light, can escape once it passes a boundary known as the event horizon. Though invisible directly, black holes reveal their presence through their effects on nearby matter and the curvature of space around them. Black holes originate from the final stages of massive stars, whose cores exceed the mass that neutron degeneracy pressure can support. When fusion ceases and the core collapses under gravity, it may compress to a point of infinite density, known as a singularity. Surrounding this singularity is the event horizon, the boundary beyond which escape is impossible. The radius of this boundary depends on the mass of the black hole and is called the Schwarzschild radius. Despite their reputation as cosmic voids, black holes do not actively draw in distant objects. Their gravitational influence is no different from that of any other object of equal mass. If the Sun were replaced by a black hole of the same mass, the planets would continue orbiting in the same paths. However, objects that venture too close to the event horizon experience extreme gravitational forces that can stretch and compress them in a process sometimes described as tidal disruption. Matter falling toward a black hole often forms an accretion disk, a rotating structure of gas and dust heated by friction and gravitational forces. As material spirals inward, it accelerates and reaches extremely high temperatures, emitting radiation across the electromagnetic spectrum. These accretion disks can outshine entire galaxies, making black holes observable despite their darkness. Jets of high-energy particles may also be launched from regions near the poles, extending vast distances into space. Black holes vary widely in mass. Stellar mass black holes, formed from collapsing stars, typically contain several times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, can contain millions or billions of solar masses. Their origins remain an area of active research, though they are thought to grow through accretion and mergers over cosmic time. Intermediate mass black holes, with masses between these extremes, have also been identified. Time behaves differently near a black hole due to the effects of strong gravity described by general relativity. To a distant observer, time appears to slow for an object approaching the event horizon. Light emitted from the object becomes increasingly redshifted and faint. From the perspective of the falling object, however, time proceeds normally as it crosses the horizon. These effects illustrate how gravity influences the passage of time and the propagation of light. Black holes can be detected through several methods. In binary systems, a black hole may draw material from a companion star, producing X-rays from the heated accretion disk. Observations of stellar motion near an invisible massive object can also reveal a black hole's presence. At the center of the Milky Way, precise measurements of star orbits provide strong evidence for a supermassive black hole known as Sagittarius A star. Gravitational waves offer another means of detection. When two black holes merge, they produce ripples in space-time that propagate outward at the speed of light. These waves were first detected in 2015 by observatories designed to measure for minute distortions in space-time. The observations confirmed predictions of general relativity and opened a new window for studying cosmic events involving black holes and neutron stars. The environment near a black hole is shaped by extreme conditions. Intense gravitational gradients can tear apart stars that venture too close, creating streams of gas that spiral inward. Magnetic fields in accretion disks can accelerate particles to near-light speeds, producing energetic jets observable across vast distances. These processes influence surrounding interstellar matter and contribute to the energy dynamics of galaxies. Although black holes are often associated with destruction, they also play a role in cosmic structure. Supermassive black holes at galactic centers are linked to the formation and evolution of galaxies. Their energy output can regulate star formation by heating surrounding gas and preventing it from collapsing. In this way, black holes contribute to the large-scale balance of matter and energy in the universe. The concept of a singularity, where density and curvature become infinite, challenges current understanding of physics. Theories that describe gravity and quantum mechanics separately do not fully explain conditions within a black hole. Ongoing research seeks to reconcile these frameworks, exploring the nature of space-time and matter under extreme conditions. Black holes thus remain at the forefront of theoretical and observational astronomy. From Earth, black holes cannot be seen directly, yet their presence is inferred through careful observation of their effects. The motion of stars, bursts of high-energy radiation, and detection of gravitational waves all provide evidence of these hidden objects. Through such methods, astronomers continue to map black holes across the universe, revealing their distribution and influence. In the quiet depths of space, black holes represent both an ending and a transformation. Born from the collapse of massive stars, they persist as regions where gravity dominates completely. Though they emit no light, their presence shapes the motion of matter and the structure of galaxies. Their silent existence serves as a reminder of the powerful forces that govern the cosmos and the complex outcomes of stellar life cycles. While many stars appear solitary when viewed from Earth, a significant number exist in pairs or groups bound by gravity. Binary stars, systems in which two stars orbit a common center of mass, are among the most common stellar arrangements in the universe. These partnerships range from widely separated pairs that influence each other only slightly, to closed systems where the stars interact in complex and sometimes dramatic ways. Studying binary stars provides essential insights into stellar masses, evolution, and the dynamics of gravitational systems. In a binary system, both stars orbit a shared center of mass known as the barycenter. If the stars are similar in mass, the barycenter lies between them. If one star is significantly more massive, the barycenter may lie closer to, or even within, the larger star. Their orbital periods can range from hours to thousands of years, depending on their separation and combined mass. These motions follow the same gravitational principles that govern planetary orbits. Binary stars are classified according to how they are observed. Visual binaries are pairs that can be resolved as separate points of light through telescopes. Spectroscopic binaries cannot be distinguished visually, but are identified through shifts in their spectral lines caused by motion toward or away from Earth. Eclipsing binaries are systems in which the stars periodically pass in front of one another from our perspective, causing measurable dips in brightness. Each type provides different information about stellar properties. Eclipsing binaries are particularly valuable for determining stellar sizes and masses. When one star passes in front of the other, the amount of light blocked reveals their relative sizes. By measuring the timing and duration of eclipses, astronomers can calculate orbital speeds and distances. These measurements allow precise determination of stellar masses, which are otherwise difficult to measure directly. Such data are essential for testing models of stellar structure and evolution. Close binary systems may exchange material through a process known as mass transfer. If one star expands during its giant phase and fills a region called its Roche lobe, material can flow toward its companion. This transfer can form an accretion disk around the receiving star, heating the material and producing increased brightness. Mass transfer can significantly alter the evolution of both stars, changing their lifespans and final outcomes. In some systems, a white dwarf accretes matter from a companion star. As material accumulates on the white dwarf surface, pressure and temperature rise until a thermonuclear burst occurs. This event, known as a nova, causes a sudden but temporary increase in brightness. If mass accumulation continues and exceeds the stability limit, the white dwarf may undergo a Type 1, a supernova, completely disrupting the star and releasing vast amounts of energy and heavy elements into space. Binary systems can also contain neutron stars or black holes paired with normal stars. In such cases, material drawn from the companion forms an accretion disk around the compact object, emitting X-rays as it heats. These X-ray binaries are among the most luminous X-ray sources in the sky. Observations of their emissions provide information about the behavior of matter under intense gravitational forces and the properties of compact stellar remnants. Not all binary interactions are violent. Wide binary systems, in which stars are separated by large distances, may evolve independently with minimal influence on one another. Their slow orbital motion can still provide valuable data on stellar masses and gravitational dynamics. Because the stars share a common origin, comparing their properties helps astronomers understand how initial conditions influence stellar development. Multiple star systems extend beyond pairs. Some systems contain 3 or more stars, bound in complex gravitational relationships. These arrangements may include hierarchical structures, where pairs orbit each other, while a third star orbits at a greater distance. The dynamics of such systems can be intricate, with gravitational interactions influencing orbital stability over long timescales. Binary stars have played an important role in advancing astronomical knowledge. Measurements of binary orbits provided early confirmation of Newton's laws of motion and universal gravitation beyond Earth. Today, binary observations continue to refine measurements of stellar masses, luminosities, and distances. They also contribute to the detection of exoplanets, as variations in stellar motion can indicate the presence of orbiting planets. The presence of a companion star can influence stellar rotation and magnetic activity. Tidal interactions in close binaries may synchronize rotational and orbital periods, leading to stable configurations. In some cases, tidal forces generate internal heating and increased magnetic activity, affecting stellar winds and radiation output. These interactions illustrate the diverse ways gravity shapes stellar behavior. From Earth, binary stars often appear as a single point of light. Only through careful observation do their dual natures become apparent. Some well-known stars, such as Sirius, have faint companions that were discovered through telescopic observation. These discoveries demonstrate how much of the universe remains hidden without detailed study. Binary systems also serve as markers of cosmic distance. Certain types of eclipsing binaries allow precise measurement of luminosity, enabling astronomers to determine distances to nearby galaxies. By comparing intrinsic brightness with observed brightness, distances can be calculated with high accuracy. This method contributes to the broader effort to map the scale of the universe. In the quiet expanse of space, stellar partnerships unfold over millions or billions of years. Whether interacting closely or orbiting at great distances, binary stars illustrate the influence of gravity in shaping cosmic relationships. Their shared motion and occasional exchanges of matter reveal a universe in which stars are not always solitary, but often bound together in enduring gravitational bonds. Although stars often appear scattered randomly across the night sky, many are members of larger structures shaped by gravity and galactic dynamics. Star clusters, vast assemblies of stars bound together by mutual gravitational attraction, provide valuable insight into stellar formation and the structure of galaxies. By studying these clusters, astronomers gain a clearer understanding of how stars originate, evolve, and move within the broader framework of the Milky Way and other galaxies. Star clusters are broadly divided into 2 main types: open clusters and globular clusters. Open clusters are loose groups of stars that formed from the same molecular cloud. They typically contain dozens to thousands of stars spread across regions several light-years wide. Because the stars share a common origin, they have similar ages and chemical compositions. This uniformity makes open clusters ideal laboratories for studying stellar evolution. Open clusters are found primarily within the spiral arms of galaxies, where star formation is active. Over time, gravitational interactions with nearby stars and interstellar clouds can disperse these clusters. As their stars drift apart, the cluster gradually loses its distinct identity. Many stars visible in the night sky, including those near the Sun, are believed to have originated in open clusters that have since dispersed. Globular clusters differ markedly from open clusters. They are dense, spherical collections containing hundreds of thousands or even millions of stars. These clusters orbit the outer regions of galaxies, forming a halo around the galactic disk. Globular clusters are among the oldest known structures in the universe, with ages exceeding 10 billion years. Their stars are typically older and contain fewer heavy elements than those found in open clusters. The dense cores of globular clusters create environments where stars are packed closely together. In these regions, gravitational interactions are frequent, leading to complex orbital dynamics. Stars may exchange energy through close encounters, altering their trajectories. In some cases, binary systems may form or be disrupted. These interactions provide valuable insights into the behavior of stars in high-density environments. Star clusters help astronomers determine distances in space. By comparing the observed brightness of cluster stars with their known intrinsic brightness, distances can be calculated. This method, known as main sequence fitting, relies on the predictable relationship between stellar color and luminosity. Accurate distance measurements are essential for mapping the structure of the Milky Way and understanding the scale of the universe. The distribution of star clusters reveals patterns in galactic structure. Open clusters trace the spiral arms of galaxies, highlighting regions of ongoing star formation. Globular clusters outline the spherical halos surrounding galaxies, indicating ancient stellar populations. Together, these clusters provide a framework for understanding the arrangement of stars and the history of galactic development. Within galaxies, stars orbit the galactic center in complex paths influenced by gravitational forces. In the Milky Way, the Sun completes one orbit approximately every 225 to 250 million years. This motion carries stars through spiral arms and interstellar regions, influencing their environments over time. The collective movement of stars shapes the large-scale structure of galaxies and contributes to their dynamic nature. The Milky Way itself contains hundreds of billions of stars organized into a barred spiral structure. Its central bulge is densely populated with older stars, while the disk contains younger stars, gas, and dust arranged in spiral arms. Surrounding the galaxy is a halo of globular clusters and dark matter, extending far beyond the visible disk. Observations of star clusters help map these components and refine models of galactic structure. Star clusters also provide clues about the chemical evolution of galaxies. The abundance of elements within cluster stars reflects the composition of the molecular clouds from which they formed. Older clusters contain fewer heavy elements, indicating formation at a time when fewer generations of stars had enriched the interstellar medium. Younger clusters show higher metallicity, revealing the cumulative effects of stellar processes over time. Interactions between galaxies can influence star cluster formation. When galaxies collide or pass near each other, gravitational forces can compress gas clouds, triggering bursts of star formation. These events may produce large numbers of new clusters. Observations of interacting galaxies often reveal bright clusters forming within tidal tails and compressed regions, illustrating the dynamic nature of galactic evolution. Star clusters are not permanent structures. Over millions of years, gravitational interactions and external forces can disperse their stars. Open clusters gradually dissolve into the galactic disk, while globular clusters may lose stars through tidal interactions with their host galaxy. Despite this gradual dispersal, clusters leave lasting imprints on galactic structure through their contributions of stars and enriched material. From Earth, some open clusters are visible to the naked eye. The Pleiades, a bright cluster in the constellation Taurus, appears as a small group of shimmering stars. Through binoculars or telescopes, many more clusters become visible, revealing intricate patterns of stellar groupings. These observations provide a tangible connection to the larger structures that shape our galaxy. The study of star clusters bridges the scale between individual stars and entire galaxies. By examining these gravitationally bound groups, astronomers gain insight into stellar life cycles, galactic dynamics, and the history of cosmic matter. Clusters serve as both records of past star formation and indicators of present galactic structure. In the stillness of the night sky, star clusters appear as delicate gatherings of light, yet they represent vast communities of stars bound together across immense distances. Their shared origins and collective motion reflect the underlying order of the cosmos, revealing how gravity shapes not only individual stars, but entire galaxies over the course of billions of years. For thousands of years, long before the development of modern instruments, humans looked to the stars for guidance, orientation, and meaning. The consistent patterns formed by stars provided reliable reference points in a changing world. From open oceans to vast deserts, the night sky served as a map, allowing travelers to determine direction and position. Beyond navigation, stars have influenced calendars, agriculture, architecture, and cultural traditions across civilizations. One of the most important uses of stars in navigation is determining direction. In the Northern Hemisphere, Polaris, commonly known as the North Star, appears almost directly above the North Pole. Because it remains nearly fixed in the sky while other stars rotate around it, Polaris provides a stable indicator of true north. By locating this star, travelers and sailors have long been able to orient themselves even in unfamiliar terrain. In the Southern Hemisphere, where Polaris is not visible, navigators rely on other stellar patterns. The Southern Cross, a constellation visible from much of the southern sky, serves as a guide to the south celestial pole. By extending an imaginary line along the longer axis of the cross, observers can approximate the direction of south. This method has been used by seafarers and explorers throughout the southern oceans. Stars also assist in determining latitude. The altitude of Polaris above the horizon in the Northern Hemisphere closely matches the observer's latitude. For example, if Polaris appears 30 degrees above the horizon, the observer is approximately at 30 degrees north latitude. Before the invention of precise instruments, this simple measurement allowed navigators to estimate their position with reasonable accuracy. The development of celestial navigation refined these techniques. Using instruments such as the sextant, navigators measure the angles between stars and the horizon to calculate position. By combining these measurements with accurate timekeeping, they can determine longitude and latitude. This method enabled long-distance sea voyages and played a crucial role in global exploration and trade. Beyond practical navigation, stars have shaped calendars and agricultural practices. Many ancient cultures observed the rising and setting of specific stars to mark seasonal changes. The heliacal rising of Sirius, for instance, coincided with the annual flooding of the Nile River in ancient Egypt, signaling the time for planting crops. Such observations allowed societies to align agricultural activities with predictable natural cycles. Stars have also influenced architecture and urban planning. Some ancient structures are aligned with specific celestial events or star positions. Monuments such as Stonehenge and various pyramids exhibit alignments with solstices or prominent stars. These alignments reflect the importance of celestial observation in ritual, timekeeping, and cultural identity. Constellations, patterns formed by groups of stars, have played a significant role in storytelling and cultural expression. Different cultures have identified their own constellations, weaving myths and legends around them. While the stars themselves are unrelated physically, the patterns reflect human imagination and the desire to find meaning in the night sky. These stories have been passed down through generations, preserving cultural heritage. In addition to mythology, stars have served as symbols of guidance and continuity. Mariners crossing open oceans relied on the steady motion of stars to maintain course. Nomadic peoples used stellar patterns to navigate seasonal migrations. Even today, the symbolism of stars appears in flags, literature, and art, representing aspiration, direction, and enduring presence. Modern navigation relies primarily on satellite systems, yet celestial navigation remains a valuable skill. It serves as a reliable backup when electronic systems fail and continues to be taught in maritime and aviation training. The principles underlying celestial navigation connect modern technology to ancient practices, illustrating the enduring relevance of the night sky. Astronomy itself grew from careful observation of stars. Early astronomers recorded stellar positions and motions, creating catalogues that laid the foundation for scientific study. The recognition that stars move predictably across the sky contributed to the development of mathematics, geometry, and timekeeping. These advancements shaped scientific thought and enabled more precise understanding of the natural world. Stars have also played a role in religious and philosophical traditions. In many cultures, the heavens were viewed as a realm of order and permanence. The regular motion of stars inspired reflections on time, destiny, and the structure of the universe. Though interpretations varied, the shared experience of observing the night sky fostered a sense of connection between humanity and the cosmos. Even in the modern era, the sight of stars continues to inspire exploration and curiosity. Observatories around the world study stellar light to understand the universe, while space missions extend observation beyond Earth's atmosphere. Yet the same stars visible through advanced telescopes can still be seen with the unaided eye, linking contemporary science with ancient observation. Light pollution in urban areas has diminished visibility of the night sky for many people. Efforts to preserve dark skies through designated reserves and responsible lighting practices aim to restore this connection. By protecting access to the stars, these initiatives support both scientific research and cultural appreciation. From guiding travelers across oceans to marking the passage of seasons, stars have shaped human history in profound ways. Their steady presence provided orientation in both physical and symbolic senses. Though technology has transformed navigation and timekeeping, the legacy of stellar guidance endures. In the quiet hours of the night, the stars continue their slow, predictable motion across the sky. Their patterns remain a source of orientation, reflection, and continuity. As they have for millennia, they offer a silent map overhead, connecting past and present through the enduring light of distant suns. The stars visible to the unaided eye represent only a small fraction of those that exist in the universe. For centuries, the development of telescopes and advanced observational tools has expanded human ability to study stars in greater detail. From early optical instruments to modern space-based observatories, each technological advancement has revealed new aspects of stellar structure, behavior, and distribution. Through these tools, the night sky has transformed from a field of distant light into a dynamic landscape rich with measurable phenomena. The invention of the telescope in the early 17th century marked a turning point in astronomical observation. Early telescopes used simple lenses to magnify distant objects, allowing observers to resolve stars more clearly and discover previously unseen celestial bodies. Though these instruments were limited by optical imperfections, they demonstrated that the heavens contained far more detail than was visible to the naked eye. Over time, improvements in lens design and manufacturing enhanced clarity and magnification. Reflecting telescopes, which use mirrors rather than lenses, overcame many limitations of early refracting designs. Mirrors can be made larger and supported more effectively, allowing telescopes to collect more light. This increased light-gathering power enables the observation of faint stars and distant galaxies. Large ground-based observatories now operate telescopes with mirrors spanning several meters in diameter, revealing stars billions of light years away. Atmospheric turbulence affects ground-based observations by causing stars to appear to twinkle. While this effect is visually appealing, it distorts astronomical images. Adaptive optic systems address this challenge by adjusting telescope mirrors in real time to compensate for atmospheric distortion. These systems use reference stars or lasers to measure atmospheric effects, allowing telescopes to produce sharper images that approach the clarity of space-based observations. Space telescopes eliminate atmospheric interference entirely by operating above Earth's atmosphere. Instruments such as the Hubble Space Telescope have captured detailed images of star-forming regions, stellar remnants, and distant galaxies. Observing in space also allows detection of wavelengths blocked by the atmosphere, including ultraviolet and infrared radiation. These observations reveal aspects of stars that cannot be studied from the ground. Different wavelengths of light provide distinct information about stars. Visible light reveals surface temperature and color, while infrared observations penetrate dust clouds to reveal hidden protostars. Ultraviolet observations highlight hot, young stars and energetic processes, and X-ray observations detect high-energy phenomena such as accretion disks and stellar flares. By combining data across the electromagnetic spectrum, astronomers build comprehensive models of stellar behavior. Spectroscopy is one of the most powerful tools in modern astronomy. By dispersing starlight into its component wavelengths, astronomers analyze spectral lines that indicate the presence of specific elements. These lines reveal chemical composition, temperature, density, and motion. Doppler shifts in spectral lines indicate whether a star is moving toward or away from Earth, providing information about stellar motion and binary systems. Photometry, the measurement of stellar brightness, allows astronomers to detect variations in light output. These variations may indicate pulsations, eclipsing companions, or orbiting planets. Precise photometric measurements have enabled the discovery of thousands of exoplanets through the transit method, in which a planet passes in front of its host star, causing a slight but measurable dimming. Large-scale surveys have transformed stellar astronomy by cataloging vast numbers of stars. Projects using automated telescopes and digital detectors map the positions, brightness, and spectra of millions or even billions of stars. These surveys provide data for studying galactic structure, stellar populations, and the distribution of elements across the Milky Way. The resulting databases serve as essential resources for astronomers worldwide. Radio telescopes expand observational capabilities beyond visible light. By detecting radio emissions from space, these instruments reveal phenomena such as pulsars, molecular clouds, and interstellar gas. Arrays of radio telescopes can be combined to form interferometers, achieving extremely high resolution. This technique allows astronomers to study fine details in star-forming regions and the environments around compact stellar remnants. Space missions dedicated to astrometry, the precise measurement of stellar positions and motions, have refined knowledge of distances and galactic structure. By tracking tiny shifts in star positions over time, astronomers determine parallaxes that reveal distances with remarkable accuracy. These measurements improve understanding of stellar luminosities and the scale of the galaxy. Modern astronomy relies heavily on digital technology. Charge-coupled devices, or CCDs, have replaced photographic plates, providing higher sensitivity and dynamic range. Digital data can be processed and analyzed using sophisticated software, enabling detection of subtle patterns and faint signals. Computational models simulate stellar processes, allowing researchers to test theories against observational data. Despite the sophistication of modern instruments, amateur astronomers continue to contribute valuable observations. Equipped with small telescopes and digital cameras, they monitor variable stars, track transient events and assist in data collection. Citizen science projects enable widespread participation in astronomical research, demonstrating that the study of stars remains accessible to dedicated observers. Light pollution poses challenges for observational astronomy by obscuring faint stars and reducing contrast in the night sky. Efforts to reduce unnecessary lighting and promote dark sky preservation help protect both professional research and public appreciation of the stars. Dark sky reserves provide locations where the night sky can be observed with minimal interference. The study of stars through telescopes and advanced instruments has transformed understanding of the universe. Observations reveal that stars are not static points, but dynamic objects shaped by physical processes. From their formation in nebulae to their final remnants, each stage can be examined through careful measurement and analysis. In the quiet observatories scattered across Earth and orbiting above it, instruments continue to gather light that has traveled for years or millennia. Each photon carries information about distant stars, contributing to a growing body of knowledge. Through patient observation and technological innovation, the study of stars continues to deepen, revealing the complexity and scale of the cosmos. Although the night sky appears unchanging within a human lifetime, the universe is in constant motion. Stars are born, evolve, and eventually fade, while galaxies shift and interact across immense spans of time. By studying stellar processes and cosmic dynamics, astronomers can project how stars and the night sky may change in the distant future. These projections extend far beyond recorded history, offering a perspective measured in millions and billions of years. Stars continue to form within nebulae as long as sufficient gas and dust remain available. In many galaxies, including the Milky Way, star formation proceeds at a steady but gradually declining rate. Over time, interstellar gas is consumed by star formation or dispersed by stellar winds and supernova explosions. As the supply diminishes, the rate of new star formation will slow, leading to a gradual aging of stellar populations within galaxies. Small, long-lived stars will dominate the future of the universe. Red dwarfs, which burn their fuel slowly and efficiently, can shine for trillions of years, while massive stars live brief, luminous lives. Red dwarfs persist as steady sources of light. As more massive stars complete their life cycles and fade into remnants, the overall brightness of galaxies will decrease, and the universe will become dimmer over vast timescales. The Sun, currently a stable main sequence star, will undergo significant changes in the distant future. In several billion years, it will expand into a red giant, increasing in size and luminosity. Its outer layers will extend far into the inner solar system. Eventually, it will shed these layers, forming a planetary nebula, while its core remains as a white dwarf. This transformation reflects the typical life cycle of a star of its mass. Galactic interactions will also shape the future night sky. The Milky Way and the Andromeda Galaxy are moving toward each other and are expected to merge in several billion years. This interaction will alter the structure of both galaxies, triggering bursts of star formation and redistributing stars into new orbits. From a vantage point within the merged galaxy, the night sky would display unfamiliar patterns, with new stellar groupings and altered constellations. Constellations themselves are temporary arrangements. The stars that form familiar patterns are at varying distances and move independently through space. Over tens of thousands of years, these motions will gradually distort recognizable shapes. The constellations known today will eventually change beyond recognition, replaced by new patterns formed by shifting stellar positions. On even longer timescales, stellar remnants will accumulate. White dwarfs will cool and fade. Neutron stars will slow their rotations, and black holes will persist as gravitational anchors. Without ongoing star formation, galaxies will become populated primarily by these remnants. The remaining stars will be small, faint, and long-lived, contributing little light compared to the brilliant populations of earlier cosmic eras. The expansion of the universe influences the visibility of distant galaxies. As space expands, galaxies beyond our local group are receding, their light stretched to longer wavelengths. Over billions of years, many distant galaxies will move beyond the observable horizon, their light no longer able to reach observers. Future astronomers in distant epochs may see a much darker universe, with fewer visible galaxies. Despite these long-term changes, the processes governing stars will remain consistent. Gravity will continue to draw matter together. Nuclear fusion will power stellar light, and stellar remnants will mark the endpoints of stellar life cycles. The universe will evolve, but the physical laws that shape stars will endure, maintaining continuity across cosmic time. The eventual decline in star formation does not signify an abrupt end, but a gradual transition. As galaxies age, their stellar populations will shift toward longer-lived, low-mass stars. The brilliance of massive stars will become rare, and the night sky will appear dimmer and less varied. Yet even in such distant eras, stars will continue to shine, providing points of light in an otherwise darkening cosmos. Speculation about the far future extends beyond current observational limits. Theoretical models suggest that over trillions of years, stellar remnants may dominate, and galaxies may become quiet collections of faint objects. Black holes may slowly evaporate through processes predicted by quantum theory, releasing energy over immense timescales. These projections remain subjects of ongoing study and refinement. From the perspective of the present, the night sky offers a snapshot of a dynamic universe. The stars visible today represent different stages of stellar life cycles, from young clusters to ancient remnants. Observing them provides insight into both past and future, revealing processes that unfold over timescales far beyond ordinary experience. The future of the night sky is one of gradual transformation rather than sudden change. Patterns will shift, stars will evolve, and galaxies will interact. Yet the overall presence of starlight will persist for unimaginable spans of time. This slow evolution underscores the vast scale of cosmic processes and the enduring nature of the physical laws that govern them. In the quiet darkness above, the stars continue their steady radiance, even as their distant futures unfold. Though their arrangements and brightness may change over billions of years, their light remains a constant companion to observers on countless worlds. The night sky, ever evolving yet enduring, reflects the ongoing story of stars across the universe. Throughout human history, the stars have remained constant companions, visible from nearly every inhabited region of Earth. Long before written records, people looked upward and observed the steady movement of lights across the night sky. These observations fostered curiosity, inspired reflection, and encouraged systematic study. Even as scientific understanding has expanded, the presence of stars continues to evoke a sense of continuity, linking modern observers with countless generations who have gazed at the same distant lights. The predictability of stellar motion provided early societies with a framework for understanding time. The regular rising and setting of stars marked the passage of nights and seasons, forming the basis for calendars. Agricultural communities relied on these cycles to guide planting and harvesting. The appearance of particular stars at certain times of year served as reliable indicators of seasonal change, allowing people to align their activities with natural rhythms. Stars also contributed to the development of early scientific thought. Observers noted that while planets wandered across the sky, most stars maintained fixed relationships with one another. This distinction led to the concept of a celestial sphere and encouraged careful measurement of stellar positions. Ancient astronomers in various cultures compiled star catalogues, recorded celestial events, and developed mathematical systems to describe the motions they observed. These efforts laid the groundwork for later advances in astronomy and physics. The enduring visibility of stars has influenced language, art, and symbolism. Expressions such as "written in the stars" or "guiding star" reflect the association of stars with destiny, direction, and hope. In literature and visual art, stars often symbolize constancy and aspiration. Their distant light suggests both remoteness and connection, bridging the gap between human experience and the vastness of the cosmos. Religious and philosophical traditions have also drawn meaning from the night sky. In many cultures, the heavens were regarded as a realm of order and permanence, contrasting with the changeable nature of the earth. The regular motion of stars inspired contemplation about time, existence, and the structure of the universe. Although interpretations differed widely, the shared act of observing the night sky fostered a sense of wonder and inquiry. In the modern era, urbanization and artificial lighting have reduced visibility of stars for many people. Light pollution obscures faint stars and diminishes contrast, making the night sky appear sparse. Efforts to preserve dark skies through responsible lighting and protected areas aim to restore access to the full richness of the stars. Observing a dark sky free from excessive illumination allows the Milky Way to become visible, revealing the dense band of stars that forms our galaxy. Astronomy education continues to connect people with the stars. Planetariums, observatories, and public outreach programs provide opportunities to learn about stellar phenomena and observe celestial objects. Through telescopes, observers can see star clusters, binary systems, and and the subtle colors of individual stars. These experiences transform distant points of light into tangible objects of study and appreciation. The exploration of space has expanded human perspective on stars. Spacecraft traveling beyond Earth's atmosphere observe stars without atmospheric distortion, while missions to other planets reveal how the night sky appears from different vantage points. From the surface of Mars, for example, the sun appears smaller, and the positions of stars shift due to the planet's location in the solar system. These observations emphasize that the night sky is shaped by the observer's position in space. Despite technological advances, the fundamental experience of looking at the stars remains unchanged. Standing beneath a clear sky, observers see light that has traveled across immense distances. Some of that light began its journey before the rise of modern civilizations. This connection across time and space offers a perspective that extends beyond daily concerns, inviting reflection on humanity's place within the universe. Stars also serve as reference points for scientific measurement. Astronomers use standard candles, such as Cepheid variable stars, to determine distances across galaxies. Observations of stellar spectra reveal chemical compositions, while measurements of brightness and motion inform models of galactic structure. These techniques demonstrate how the steady light of stars can be translated into precise scientific data. The presence of stars in the night sky provides continuity amid change. While individual stars evolve over millions or billions of years, their collective appearance remains stable on human timescales. This stability allows each generation to share in a common experience, observing familiar constellations and patterns. Even as the universe evolves, the night sky offers a sense of permanence and shared heritage. Modern technology enables the capture and sharing of stellar images with unprecedented clarity. Digital photography and online platforms allow people worldwide to view detailed images of star clusters, nebulae, and distant galaxies. These images extend the reach of observational astronomy, making the beauty and complexity of the cosmos accessible to a global audience.